Okay. See if I can. Just give me 1 second, guys. I'm trying to connect my iPad. Can everybody see the screen?
We can see it, Dimitri.
Okay. All right. So this is basically a mini review thing I made for you guys' exam too. I really got over the notes over the weekend to just got this all together. So I'll just start off with just this, and it has some problems too that I'm gonna solve. So let me first start off with angular momentum. So when he taught you about angular momentum, he was talking about like the cross product between position and momentum. And throughout the lecture, he was just basically teaching you commutator techniques to use to like solve some problems. So the stuff you learn is pretty much commutator problems and the relations you get from it. So first off, definition of angular momentum is position of it's the cross product between position and momentum. And use cross product like this. If you guys took either linear algebra or anything or Calc 3, you would know that this is how you do cross product here. And you don't need to know for the exam. It's just like how you get the relations below. So this is so each of, when you do the cross product, you get these 3 terms, and this relates to the angular momentum in the x direction, angular momentum in the y direction, angular momentum in the z direction. And if you can transform these terms into operators. So when you turn them into operators and you do cross product, I mean not cross product, but you do commutator relations, you find that if you were to do a commutator of one direction to the other, you'll get IH bar times the operator of the other direction. And if you do this in reverse, it'll be the negative of that. And so that's what you need to know for if you're doing a problem and it's asking you to find and in between the problem is asking the commutator between these two. You just use like these here and like have it in your notes like written down so you can like write it down. And this makes sense because you can't measure the commutator, you can't measure the angular momentum in the y and x direction simultaneously because you're doing one rotation and you're not doing the other rotation. And it's written down like right here. Okay, and let's point out this. Okay. And then from here, you see that if you do the commutator with the angular momentum squared, it's just going to be equal to 0. And you use this by using this relation. And okay, so now we get into the important stuff. So if you apply the operator, like let's say you apply the LZ operator onto a wave function, you'll find that is determined by a quantum number m. And when you go into H like atoms, you know the m quantum number, you can pretty much just find what the LZ is by just using m and plugging in. And to find the angular momentum squared, you just have to plug in the L quantum number and multiply by H bar, and that will give you the angular momentum squared. And if you want the angular momentum itself, you just have to You gotta take the square root of each side, and then you'll just get the square root of L plus L times L plus 1. Let's see what else. And the projection angle on the L makes with the z-axis is literally this equation. As long as you know what M is and you know what L is, you can just solve what this is, and then you just do the arc cosine at each side to find the angle. Okay, what is the value of the commutator J, Y here? Okay, here's the first question. I think this is on your my old exam, but how you would approach this, just give me 1 second. Pull out the question. Okay, so how would you approach this problem is pretty much just, okay, the component, what is it? So JY is just pretty much just saying the same thing as as the same thing as LY. And so you can use from you can use the commutator relations, you can find what Ly is equal to, and you could just like plug in. So let's simplify the commutator. So and then you apply an arbitrary function, and you'll find that this is equal to I believe that's F minus, and then that's equal to F. And what you would do is this isn't just equal to Ly, you would just get this right here. Times Z and the function here. Okay, and then from here you would just distribute, and you would find that this is just, now you can put this next to the other. So the thing about this, the tricky part is that P of X is basically just a derivative, and since Z is a constant and this is derivative in terms of X, you can put this outside, so it will be Z and then Z and then PX minus, but since the derivative is on the right, this is a derivative in terms of Z, you have to put this like on the right of it. So you can't take this out. So this will be X operator, PZ, and then this will be Z, and then F. And this will be minus Z, PX, the F here. Okay, and this is F minus X, PZ. All right, and then from here, we would just see what we can like cross out. So this can cross out with this. And the only thing we're left with is this here. You can't pull out z in front because the derivative, this takes derivative here, and this is z variable, so you can't take this out of it. So what you're going to be left with, if I take a negative out, we have, oh wait. You have to take the negative out, we'll have we take f out. This is f. All right. And then from here, we would find that this is going to be equal to okay, let's see. This is going to be equal to L. Oh, wait. I did this correctly. Oh, yeah, now I remember. So this is just if you simplify out the x, then this is just p z p z. And this is just a commutator for pz and then z. And this is just going to be IH bar. I think I wrote that note here. So yeah, this would be, I didn't write the note here, but since this is, it's pretty much like the same thing as px and x, which is negative IH bar. And so this is just going to be equal to negative x times negative IH bar, which will just be IH bar x. Does that make sense to everyone? Anyone have any questions or anything or in this question?
I have a quick question.
Yeah.
Why did you take out the operator symbol?
Oh, you mean x here?
Yeah.
So I took it out so I can put it into terms I understand. I took it out because I can find out that this is a commutator that we calculated before. So up here, if I can take out x because it's only that's only the momentum operator. Momentum operator is basically just the derivative, and x is just a constant. So you can take that x out, and then afterwards I keep x out so I can find out that this is a commutator, because if there's a definition of a commutator, it's just the operator first, the first operator onto, and then the second operator minus the second operator and the first operator. And so I found out this is a commutator that we calculated before, which is just equal to this negative IH bar. And that's why I take x out, because I have a term that I could put it, I took the x out so I could find out this is a commutator, and so I can then plug in. Does that make sense?
Yeah, I understand that. I meant like, why is there not a hat here?
Oh, I think I forgot it.
Oh, okay.
Yeah.
Thank you.
Yeah, I forgot the hat. Okay. All right. Now, does anybody else have any other questions? Okay. So let's move on to the rigid rotor. So rigid rotor is basically just means that there's two, like let's say it's a diatomic atom that has two masses onto each other. Let me get so it's and it rotates by the center, by about the center of mass. And it has no translational energy. So when it rotates, it's going to have an energy, and this energy is determined by a quantum number called J. And if you're given a question, it can either be like J or L. Just do this problem the same way and just replace the variables. So it can be like L and L plus 1. Pretty much, it can be the same thing. All right, so then what you find is when you, it's determined by the quantum number J and multiply by these terms here. And during that lecture, you're given a term, it's called the rotational constant. And sometimes they give you the rotational constant, so you don't have to worry about this at all. But other times they don't, and they expect you to calculate it based on h bar, which is just a constant that's given to you, and I, which is determined by the radius, so like the radius from its center of mass, and also the reduced mass, which is just used by this equation here. Okay, and to find the degeneracy of the quantum levels, you'll find that you can use 2j plus 1, and you can just plug in whatever j value you have to find the degeneracy of that level. And if you're given a question that tells you what is let's say, what is the rotational constant B, you can what you found is that you can also minus it from each other. So J plus 1 to the energy level above to the final after it's like been excited, minus the initial, which is D of J. And then what I found is you can calculate it like this. This is just basically plugging in and finding out this is it for two energy, like a space between two energy levels is determined by this. And so basically you can, let's say you're asking you, what is the frequency from this transition from like the upper transition, like that's like increases by 1 level. You can pretty much use this this is just Planck's constant, and this is just the frequency. So let's say you're trying to solve for it, A given B, you just like plug in the previous J level. So let's say if it was J1 to 2, you plug in J1 because that's the previous level, and then you would solve for it. Or if they're asking you to calculate the B constant, then you would just plug in 1, and then you would just put this on the other side if you're given the frequency also. Okay. Let's see. All right, and this is just an example from my exam last year. So let's see. Consider the time to what is the difference between energy flows from J10 to okay. So based on our equation, we can just calculate this. So it's just equal to J and J plus 1 times B. And you really want E rotation of J10 minus E rotation of J6. And this is just going to be equal to 10 plus 1. I can just keep B on the outside. Minus 6 plus 1. And times B, which is 25.5263 centimeters. Let's get out the calculator. Plus 1. It's 25.5263. There's good. And you'll find that this is equal to 1735.7884 centimeters to -1. Does anyone have any questions about that? It's pretty much just plugging in and chugging. So just basically plugging in for 10 and plugging in for 6 and subtracting by each other. Okay, part B.
Sorry, can you zoom into the actual problem? I can't really see it.
Oh, you mean, oh, this one here?
Yeah, thank you.
No problem. Okay, so the next part is tricky. So it's telling you that this time you have a diatomic atom that's similar to the one you just used to calculate the energy difference. The only difference is that the new mass A, is 0.085 times the old mass A, and mass B is 0.85 times mass B, and its bond length is 0.913 times Ra. It's asking what is the energy difference between the energy levels of J9 and J7. And so what you do here is you just, I'll just start off. So let's first start off with what B is equal to. So B is equal to, based on the previous, is equal to h bar squared over 2 times m. This is Ra. I mean, yeah, I mean AB. Squared. Sure, that's right. Yeah. And so if we were, let's say we were to plug in, so M, the new reduced mass is equal to MA, MB, plus MB. Now, if you let's say we plug in what happened in the problem, so we would find out that this is equal to 0.85 times MA, and this is from MA, and this is 0.85 times MB. And this is all over 0.85 times MA plus 0.85 times MB. And what you would do is you would distribute out this, so you have the old reduced mass. So you would distribute this out, and you'll subtract, and you would multiply this, so 0.85 squared, which would equal to 0.7225, and this is times MA MB. And this is you just distribute out 0.85, so you just have MA plus MB. And if you solve the outside, you'd get this equal to 0.85. And this is just the old reduced mass. So this is just going to be 0.85, that reduced mass. And that's what the new reduced mass is going to be. It's going to be 0.85 of the reduced mass. And next, what you would do is you would solve for RA. So in this case, we found out that B is equal to h bar squared times, this is the new one, 2 of times RAB squared. And what you find is this is equal to h bar squared times 2. And then from what we saw before is 0.85 times the old reduced mass, and it's times RAB. Oh, it is 0.913 RAB squared. This is what this is equal to, and from the problem, this is what this is equal to. And then this is just going to be equal to h bar squared and 0.913 squared times 0.85. This is just 0.708. 0.8 times 2, the old reduced mass, and times RAB squared. And then from here, you'll find that this is going to be equal to B, since this is just all. I mean, this is old variables. To get the old reduced mass is just going to be equal to B. And so what you're going to find is that the new rotational constant is going to be equal to 1 divided by, let's put this to -1. This is going to be equal to 1.411 times the old reduced mass. And this is just going to be equal to 1.411 times 25.5263. -1. It's just 36.0269. And that's the new rotational constant. Does anyone have any questions about this? Okay, so what I pretty much did was I just put it into variables that were used to get into the new rotational, to get to the old rotational constant. So I put in the terms I understand from the previous problem, and then right there I distribute out everything to what changed. And what changed is now that you have these new values for RAB and MA and MB, you're going to have this value be multiplied by the old rotational constant to be this new rotational constant. And let me just double check if I got that. Second. Okay, so then it's asked to calculate the using this new rotational constant. We're going to be asked to calculate the new energy difference between 9 and 7 from J. So this will be 7 minus E rotational. Oh wait, that's 9, and then that's the rotational 7. This is just going to be just the same equation. And times that new rotational constant. Yep, and this is going to be equal to 1224.92 centimeters. Okay, does anyone have any questions before I move on to the next part?
So does E just represents energy, right?
Yeah, just energy.
Okay, and then B is can you just explain what B means again?
Oh, B is the rotational constant, and you can from what I've saw about in my notes that it's equal to this equation. And what I basically did was I backtracked and I calculated based on the new values they give us. So we're based on the reduced mass, which is in the inertia equation, which is right here. This is just the movement of inertia, and I just expanded it.
Gotcha. That makes sense. Thank you.
All right, no problem. All right, so let's move on to the bulk of your what's going to be on your exam. So H-like atoms, so stuff like hydrogen, deuterium, all that stuff that only has one electron is going to from their lecture, it was found that you can solve it with with the wave function of this. So this is going to be made of the radial wave function times the angular wave function. And why this is because when he solved this in lecture, he used I believe spherical coordinates, which is just rate, which has three variables, which are r, theta, and psi. And from solving these, he also found that the wave function can exist in different quantum numbers and different just different quantum numbers. So like N, L, and ML, or it can be M, but I put ML because you're gonna have to do with also MS, which is just spin, but I'll talk about that later. And that's just a magnetic quantum number. So the N can exist, but it can exist to 1, 2, 3, which are just integers, basically just like particle in a box. L cannot exceed N cannot exceed what L is for what N is, and ML can exist in any common numbers depending on L. So let's say if L was equal to 1, then it can the ML can be like -1, 0, and then 1. So it depends on L, and L can't be over n-1. And this is why there can't be any 1p orbital, which makes sense. So then you guys know basically how you name these based on the orbitals. So if you're given that the M, for example, like below, let's say you're given that these are the three quantum numbers you have for the wave function, then you're going to find that this is going to be, so it's going to be 2. So it's going to be a 2 orbital, which and then it's going to have 1, which relates to a p orbital. And because it has a quantum number of 0, that means that the M is going to be 0, which means it's going to be a 2p0 orbital. And if it was in the reverse, like a 1s orbital, then it would be, this will be 1, this would, this would be 1, this would be 0, and this would also be 0 because it can't, because the only value that M could be is 0. Okay, let's see. And this number of spherical nodes are equal to the value of L. So a p orbital has 1 spherical node and a s orbital has 0 spherical nodes. Radial nodes are basically depending on L. So if you're talking about a 2p orbital, it's going to be 1 minus 1. So n minus L. So it's 2 minus 1 minus 1. All right, I'll just think to go back to this later, but all right. So he solved in lecture, he solved this by finding out, he found all this facts out by solving the Schrodinger's equation in spherical coordinates. And after solving it, of course is going to be a the wave function of an H-like atom is going to be a eigenfunction of the Hamiltonian operator. If you apply the Hamiltonian operator, it's only going to be dependent on n. So that basically means if you know the radial part of the wave function, you don't need to solve, you don't need the spherical. So let's say it'll give you the radial wave function. You can just use this radial wave function, and based on what this value is, you can solve for the energy of that system. And so below, you'll find that the equation can be equal to this. And this is just in ergs, this is in joules, and this is this is in electron volts. Electron volts. And what really gets tedious about this is just solving it. Like because the hardest part about like solving for energies is just putting all the constants onto your calculator. So he also made a different way of solving it. I mean, he didn't make this different way, but he explained a different way, which are called atomic units. And I forgot to write this down, but atomic units just means that you just need z squared and 2n squared. And this is going to be the atomic units for this is Hartrees. And if you guys are like on the test, I would suggest you just use Hartrees if he taught it to you before, or ask him if you can just use Hartrees because it makes your job a lot easier when solving these problems. And so all you need from Hartrees is just Z and N. So the charge of the proton and the quantum number N. Okay. And since this is just an explanation to the reduced mass, but basically the reduced mass is just going to be equal to m, the mass of an electron, because the mass of electron is so small that it's just going to, this term here is negligible. And so the MP is just going to cross out and it's going to be left with the mass of electron. If you want to find the degeneracy of a orbital, like let's say they give you just N, you just square N and find a degeneracy. And the ionization potential is the amount of energy required to remove that electron. And so it's just going to be the negative of that energy you calculated. So if you were trying to calculate this, and I don't know what negative here, but if you're trying to calculate the, let's say, the ionization energy of a 1s orbital of hydrogen, you would just use, like, for example, this equation here. You would plug in, let's say, I mean, charge of hydrogen is just 1 squared, and 2n, that's going to be a 1 orbital, so it's going to be 1, just going to be negative 1 over 2. But since it's a negative, it's going to be 1 over 2 Hartrees. Okay, so there's also energy level transitions. So if they ask you, what's the next energy level, what's the frequency of the photon emitted when this electron jumps to this energy level or goes down to energy level? So that's going to be you basically subtract these two equations and you just use this here. And if you want to just use Hartrees or something, you can just like negate these terms here and then just like solve for it. So if it's like from a 1, I think like a 1 to a 2, then just plug in 1 here and you'll find what the energy level transition is and solve for F or solve for the wavelength based on what they ask you in the question. Okay, so the first question is to predict the ionization energy of beryllium 3+ in its ground state given by the ionization energy of Li2+ in its ground state 122.45 electron volts. Notice that the numbers of the proton, neutrons, and nuclei make their nuclear masses efficiently infinite compared to the mass of electron. Okay, predict the ionization energy of lithium 2+ its ground state. Okay, so what they want you to do for this is they want you to they give you the ionization energy for lithium, so you can use that to like calculate the constants. So he just helps you solve this in fewer steps. So we know that the ionization, say the ionization potential for lithium is just going to be equal to, let's say all these constants here, I just put into like one variable, and it's called variable W. And it's just dependent on z squared over 2n squared. And they give us the energy for this, and it's going to be 122.45 electron volts. And the charge of lithium would be about 3, and in its ground state, which means it's in a one orbital, I guess a 1s orbital. So then this would be W times, that's okay, 3 squared over 2 times 1 squared. 122.45 electron volts. And so this is going to be equal to 9 squared over 2 W and after, no, let me move the squared here. No. Okay, and after multiplying my 2 over 9, you would get that this is equal to 27.21 electron volts. And basically what you're supposed to do is use this constant to find the answer. And so let's see, ionization of beryllium 3+. And this is going to be 27. This is just the constants here, times c squared, which is 4 over 2, and it's ground state, so it's going to be times 1 squared. And then it's going to be 217.69 electron volts. And this makes sense because it takes much more energy to remove an electron that has a higher nuclear charge. So because it has a higher nuclear charge of 4 in comparison to 3. Okay.
I have a quick question.
Yeah, what's up?
What is W again?
So I just made up something to just calculate that constant. So like the W is basically, okay, let's do it. It's just basically like all these constants together.
Gotcha. Oh, wouldn't that depend on the charge of Z though? And here we have different charges.
Oh, it does. That's why the charge is right here and the end's right here. So all the other stuff that doesn't depart. That
Oh, I
doesn't,
see. Okay. It's all the other constants.
yep,
Gotcha. Thank you.
no problem. And I just realized if you calculated with this here, you'll be perfectly fine. But this is just in case you don't like have like anything like that. Like so next part is to calculate the ionization energy expressed in atomic units for a 4p orbital in an electron state. Okay, so the only thing different, okay, is B, it's 4p, okay. Ionization of lithium 2+, it's 4p orbital, which would be, so we found out this is 27.21 electron volts times, it would be still a charge of 3 squared, and then that's 2 times 4 squared. And this is 2 squared, so that's like 9 squared 27.21 2 times 4 squared. This would be 68.88 electron volts. And that's all I did for part B. Now, does anyone have any questions?
So ionization energy isn't really dependent on the sublevel, right? It's just mostly dependent on like the principal energy level.
I wouldn't say, I guess it is. I mean, I wouldn't say that because the higher the L level is, it's gonna mean the ionization energy is less. So for a 4p orbital, it feels less of a pull to the, I mean, I want to say, yeah, I guess it feels less of a pull to the nuclear, to the nucleus. Because if you compare this to what we calculated before, lithium, this is much more lower, which means it'll be a lot easier to remove the electron at a higher energy level. I mean, yeah, and value, yeah. Does that make sense?
Yeah, thank you.
Okay.
I have sorry, a quick question as well. The 4py that you just multiply the original number by 4. Is that what you do?
For part B,
Yeah.
I use the same equation, but this time I replaced n with instead of n equals 1, n is equal to 4. So it's divided by 4 squared instead of divided by 1 squared.
Okay, gotcha. Thank you.
All right, no problem. All right, so for the next part, it's gonna be asking to calculate expectation values and most probable distance. Now they never asked me to calculate the most probable distance. I'm gonna probably save the next questions for the end, like these two. But basically, so like the radial probability is just since you're dealing with spherical coordinates, you're gonna have to have the r squared here when you integrate. And so the radial probability is just r squared times the radial the radial wave function squared. And when you're trying to find the most probable distance of an electron, you have to take the derivative of this, of PR, which is just this. Just put that as P. And then you have to solve for 0. Because at the maximum, the derivative is equal to 0. And that's why you have to solve for R, like here. This is the graph of the radial probability. And to save on time and also to save on save with time, but you do product rule and stuff. My professor in physics taught me that you can just literally take the square root of this and just multiply r times r of n, so that it's a lot easier to take the derivative of it. Okay. So like I said before, everything's in spherical coordinates. So when you're dealing with spherical coordinates, you're gonna have to do like r squared here. These are the volume elements and sine of theta. And I never ever heard in my ever had to deal with integrating something like this, only on like homework, but never on a test. But this is just something to have, just in like, I don't know, like just in case for like a volume element or anything. So you this is just if you're trying to calculate expectation value and it's dependent on, let's say the expectation value is dependent on theta and the rate and r. But if it's not, and it only depends on r, like r squared and r, which is right here, you can calculate it by this. So the operator onto this, so this will be r, and this will be p r of n, r of nl. And you just need the radial probability just to calculate that. You don't need the rest of the terms. So you just have to solve like one interval, and let's solve 3 intervals. And if you're trying to find the probability between 2 different regions, let's say G is given, you just solve it by just solve an integral r squared, just basically a probability of P of r, and then you just plug it in and you just find the probability. But if you not given the probability, and I mean you're given the probability but you want you to find G, you just solve it the same way, but this time you plug in G as a variable and just solve for G. And I'll just solve these at the end because these get like really long. And I'll move on to the next part. Okay, so this is something that's definitely going to be on the exam. It's called Dirac-Ket notation. So Dirac-Ket notation is just a simpler way of writing integrals. So that way you don't have to like write like a bunch of stuff. So for here, I just wrote it here. So like this here means that there's a complex conjugate, which is right here. and you find an expectation value, the operator's in the middle, and on the right is the right term that's what the operator operates on. So from here, and the volume, since these are volume elements, these are included in the interval, so you don't have to write those in. Okay, and it's the same thing for the angular wave function. And so since it's a simple way of writing intervals, if n and l are both equal to each other and they're both normalized wave functions, the radial wave function, when you integrate and you put in this notation, is equal to 1. If n or l is different, this will equal to 0. This means it's mutually orthogonal, meaning that they have different eigenvalues. And they have different quantum numbers, if they have different eigenvalues, these means they have different quantum numbers. So because the different L will result in a different eigenvalue, meaning that they're going to both be orthogonal to each other. And even if one's different and the other is the same, they're going to be orthogonal to each other. Let's see what else we got here. And we have, oh, it just means when you operate an operator that's an eigen, this is the eigenfunction of that operator. That means you'll produce a constant, and a constant will be pulled out, which means you'll be left with these terms that are both normalized, and they both have equal n and l. This will just equal to 1, and you're just left with the expectation value. And if you operate on the operator, and oh wait, just fix that. If you operate an operator, you're going to be having a constant on the outside, but since this is a different quantum number than this here, then that means they're going to be orthogonal to each other, which means this term is equal to 0, which means this interval is going to be equal to 0. All right, so let's move on to the questions. So what are the values of the following intervals relevant to the description of hydrogen atom? In each case, provide work that justifies your answer. If the answer is written without work or explanation, it won't be counted. Okay, so the first part of this is pretty easy, but what you do for this, I don't know why Ranieri or Sears does this, but he always puts a trick in one of the questions to just check your knowledge. Okay, just put this here. So what you do first is to check your quantum numbers. So you make sure based on, I'm just gonna copy and paste the rules. Where is it? There we go. Okay, so what you do here is that you check the quantum numbers. First, you check if L is going to be less than the n quantum number. So this is L. You want to make sure this is less, and right here this is less, and M is not over L. So this is not over L at all, and this would have an integer. I forgot to mention also, this is just spin. So we make sure that these are half integer spins, because if you guys remember, electrons have integer spins, and that makes sense here. Oh, but this here and this here on the other term are not equal to each other. So this wouldn't make, this wave function doesn't make sense. And this is because L is greater than, not L, L is equal to N, and it has to be like 1 less than N, its maximum. So it has to be something like 3, 2, or 1. Does that make sense to everyone? So basically that means we wouldn't solve this interval at all because of this term here. This can't be a wave function. So to save on unnecessary work, just always check that. Okay, let's go to B. Okay. This time I'm gonna copy this. All right, from looking at this question, we see that these follow the rules. These have half integer spins for the electron. And also this is lower than L. And it's like it just doesn't go over L for M. And L doesn't go over N. And these are all equal to each other, like all these column numbers. So that means these are going to be the same wave function, meaning that this is going to be equal to, if you apply the Hamiltonian operator, we know this is the eigenfunction of the operator. This is just going to be equal to E4. And since these are normalized, it's going to be left with 1. Now, does that make sense to everyone?
Oh, can you just repeat what you said?
Okay, so what I'm pretty much saying is this is an eigenfunction of the operator. So I can apply the operator onto this and I can get a constant out, right? So after applying that constant, we're just going to be left with this here. So after applying the constant, we're just going to be left with these terms. And these terms are this is normalized, which means this is going to be equal. This interval is going to be equal to 1. And I'll just write it out. I'll solve it here. So this makes sense. So this is just going to be equal to 1 because these are normalized. That makes sense to you?
Yep.
Okay.
All of the quantum numbers have to match, right?
Yes, all the quantum numbers have to match.
Including the spin?
Yes, including the spin. If one didn't match, then this interval will be 0.
Cool, thanks.
Okay. So from here, you would just plug in 4 and you would solve for this. Is this for a hydrogen-like atom? So what did I give in Z? So just solve this, and I'll just solve this in Hartrees. Z squared over 2n squared, which is just 2n is 4. And this is going to be equal to Z squared over 2 times 32. Hartrees. No, give us, oh guys, give me 1 second. All right, sorry about that. I'm back. All right, so we'll move on to part C. Just all right, so from here, we see that all those column numbers match. All these match here, and we're applying JZ. So from the JZ is literally just LZ. So after applying this, we can find that this is equal to, we can solve JZ by just having the quantum number for M. It's going to be M H bar. And we found that this is going to be equal to negative h bar, because that's what m is equal to here. Okay. Oh wait. Yeah, that's it. That's it. Okay. And since we're going to be left off with a constant, because this is just an eigenfunction of the this is the eigenfunction of the operator, we're just going to be left with negative h bar times 1 because they're normalized, and this is going to be equal to negative h bar. Now let me just check if all these column numbers match. Okay, they do. And let's triple check on okay. Yeah, okay. And go up. All right. So from here, we can move on to part D. Four, three. Okay, from here, we can see that this is going to be different. And I forgot to also mention about the spin operator, which is just operates onto this to get the spin, which is right here. And it's in the same equation. So you just use JZ. And this is just going to be equal to MS, which is just a spin quantum number. And this is times H bar. And the spin here is going to be equal to 1/2. This is H bar over 2. What else?
So J represents the third quantum number, and SZ represents the fourth quantum number, the spin, right?
Yeah, sure. JZ represents the third quantum number. Yeah.
All right, gotcha.
Yep. Let me put ML or MJ. So let's put MJ. Yeah, or it can be ML, depending on what they use for it. But it's either J or L. In this case, it's J. Does that make sense?
Yep.
Okay. All right. So next part they say. Okay. First, I forgot to also say that first we need to check if the quantum numbers make sense. So from here, just check the sheet. 3, 1, 9, 3, is less than 0, which is not possible. Oh, yeah. So from here, I'll just pull out L. So L can't be negative at all. So from evaluating this, we found that L is -3, and this is not possible. Not possible to be a wave function. So we wouldn't solve this at all. All right. Does that make sense, everyone? Okay. Go on.
Wait, hold on. Why would it be possible?
Because L can't be negative. Right here, L is
Okay. Oh, okay. Yeah, that makes sense.
I was gonna do some more examples, but it'll be kind of repetitive. So I'll just save it for later if you guys want. Okay, perturbation theory. Perturbation theory is basically like, okay, the Hamiltonian we have can't accurately describe the system we have, so we have to like add another term. In this case, it's the first order correction, which means it corrects the Hamiltonian we have currently. So right here, it can be, this is the first correction Hamiltonian. So, and I'll show you guys examples of permutation later on, but first order correction will go to the second order. And this is true for the wave function too. If the wave function doesn't accurately describe our system, we can expand it to other terms. And I don't think you don't have to worry about that. You have to worry about just the Hamiltonian term. So let's say you want to calculate the correction of the energy. Then you would apply that additional Hamiltonian term, that first order correction, and you would solve the integral of it. And this is just going to be the first order correction. So it's basically just the total energy is just going to be equal to let's say E0, which is just the if I were to solve it with the original Hamiltonian, and this is going to be plus that first correction, and that corrects energy for that specific system. And I'll show you guys examples for some in a few. Okay, so first I'll talk about magnetic field and spin. So the wave function for like for H-like atom also includes the ms term, which describes the spin of the electron that's in the system. And and this here is the spin wave function, which can either be alpha or beta. And so the wave function, the full wave function will be but the full wave function will be like a N L M L then MS, and this will be made up of the spatial wave function. Yeah, this will be made up of the spatial wave function and the spin wave function. And the spatial is just like R or all the other angles. So the spatial wave function includes the radial wave function and the angular wave function. So it's just R, theta, and psi. And the other term is just a spin wave function, which is just describes the spin. So it doesn't really have any terms. And this can be either spin up or spin down. And if it's spin up, it's designated by alpha. Spin down, defined by beta. And when you operate the operators on these terms, like SZ, you'll find that this is just 1/2 positive for times h bar, which means spin down, and negative 1/2 times h bar. And it's determined by the ms column number. So if the ms column number is 1/2, like positive 1/2, it will have the alpha wave function. If it's negative 1/2, it'll have the beta wave function. And the total spin angular wave function is pretty much like the total angular momentum wave function. It's pretty much just you plug in whatever spin you have. But in this case, I think in almost any case, it'll just be 1/2 because it'll always be positive. And it's the same for alpha and same for beta. So they both have the same total spin angular momentum, which will be this term here. By h bar. Oh, times n times h bar squared. H bar squared times beta. Okay. All right, and so let's talk about magnetic when electrons are in a magnetic field. Now, when electrons in a magnetic field, it splits in energy based on its magnetic column number, so ML here, and its spin column number, which is MS. And after you apply the column numbers, they'll split in energy, like after a magnetic force is applied to them. So like B in this case. And this will be, in this case, this is the first order correction. And normally, if the magnetic field is not turned on, so this B will equal to 0, which means the energy is just equal to the energy of the electron, like normally, like the original, like Z squared over 2n squared. Okay. All right, let me just pull up recitation 7. I don't really think that you guys are going to have any questions in regards to like stuff like magnetic, because like the number of constants and stuff is just like too much, but you can never be too careful. Okay, recitation 7, number. Oh, there we go. Do you guys still see my iPad screen?
Yep.
Okay, thanks. Okay, so how you would solve this is you would use this equation here. So hydrogen atom in its ground state when energy -1/2 Hartrees. If this electron was subjected to an applied external magnetic field of 10 to the 5th Gauss, by how much would the 1s state of the atom change? So since this is a ground state, and this is going to be a ground state is going to be when S is going to be a 1s orbital, that means that ML is going to be equal to 0. So that will mean that you don't have to worry about that. And the rest would be so this can split. So we don't know that's the charge, I mean not the charge, the spin of the electron. So this can be either -1/2 or 1/2. So we can have two terms here. So this could possibly be, so I'm just going to include this here. And or this can equal to
Are you writing on the screen right now?
yeah, you don't see it?
Nah.
Okay. All right. Let me stop my sharing and share again. There we go. All right, you guys can see it?
Yep, thank you.
Thank you. All right. So what I was basically saying is you would use this equation here. So for magnetic field and spin. And from here, since this is a 1s, the electron in the 1s orbital, that means that ML is going to equal to 0 because L is equal to 0. And the only value that ML could be is 0. And from here, we would just find what this is equal to, but this can be either spin up or spin down. So because of that, we have to do two terms and find out what these are equal to. So let me find out what the constant is. So R. Okay, so this would be, I believe, in Hartrees, this would be -2 times 2.1272 times 10 to the negative 10 Hartrees over Gauss. And it's for that term, and we multiply that by the amount of Gauss applied, which is 10 to the 5th. And we multiply it by the Plum number -1/2. Hopefully I solved this correctly. 272 and this times 10 to the negative 10. So okay. Times 10 to the 5th. And that's times -1/2. So 2.1272 times 10 to the -5 Hartrees. And since the only thing different about the other term is it doesn't have a negative sign, this will be -2.1272 times 10 to the -5. And let me just double check if I got that correct. Okay. Yeah. All right. So this is the change that will be applied. So this can be either, so after plugging this in and finding the new energy, which is En plus, we're going to have two terms. So this would be E100, and this would be 1/2. So then we found to be -1/2 Hartrees. And that's subtracted by 2.272 times 10 to the -5. Which is 0.50002 Hartrees. If it was spin up, if it was spin down, and I'll just put that on the next page. And this week, and 2 times 10 to the -5. And then that will just be equal to, oh, it's plus, and that's just -0.49997 Hartrees. So you're gonna have two energy levels that split. All right. Does anyone have any questions about that? Just by the negative. All right, if no questions, I'm gonna move on to the next part. And this is for multi-electrons. So let's say you have an atom like helium or anything above like 1 electron. You're gonna have to find the Hamiltonian for it, but you can use different terms. So like, let's say you can use the kinetic energy of the electron, or the potential energy to electron to the nucleus, how much it attracts it. And the new term here, which changes things like 1/r ij, which just describes the interactions between the electrons to each other. And what you have to do is you can't count interactions twice. So let's say for helium, you only have one term for electron 1 and electron 2. So you can't count an interaction between electron 2 to electron 1 because that interaction is already counted. So for helium, that's why we have one term here, R1, 2. And because we have 2 electrons, we have to use two ways of two coordinate systems. So this will be a coordinate for R1 and a coordinate for R2, because it describes electron 1, electron 2 to the nucleus. And this is just the kinetic energy in terms of 1 and 2, which will just be derivative terms in terms of electron 1, electron 2. All right. So based on that, let's go to Fermi Dirac. So what they found is that this is a good way to explain interactions, but we also have to explain, we have to also get a wave function. And they found that the wave function that we had to make has to be anti-symmetric, because electrons are fermions, which means they don't occupy they have this integer spins, and they have and if you were to, let's say you have 2 electrons, if you were to exchange them and replace them in space, their wave function must be negative as a result. And this will go more in detail on the next page. I'm going to show it, but so this is the an operator that does the thing I was talking about. It transfers electron 1, the terms that are in terms of electron 1, terms of electron 2, and they switch it, and this results in the wave function to be negative. And this means that it's anti-symmetric, which is what we want for an electron, because they're fermions. And basically what I just said, it must be asymmetric with respect to exchange of space and spin coordinates. And one wave function must be anti-symmetric for the whole wave function. So, well, like I was saying before, the wave function that's explained is that this is the spatial wave function. And this has the radius, also the radius, the angular parts and stuff like that. While this has the spin, so it could be either alpha or beta. And the spin wave function can be a whole bunch of terms of alpha and beta. For example, right here, we see that this is the terms of alpha and beta. And as long as one of these wave functions is anti-symmetric and the other one is symmetric, then the whole wave function is anti-symmetric. And this will go into detail down here. So let's say that we're trying to see if this wave function here, this spin wave function is anti-symmetric. What we do is apply the operator that exchanges space. So then this would be 2, and this would be 1, and this would be 1, and this would be 2. And if you look at the original term, this would be negative of the original spin wave function. And because of that, this would be anti-symmetric because of that, after applying the operator from looking and observing here. And The next is the spatial wave function, and the spatial wave function can be described like this as a multiplication of 1s1 and 1s2. If you apply the 1-2 operator here, this would be the same. So this would have a plus sign, and this would be symmetric. And symmetric times anti-symmetric would be anti-symmetric. If they were both anti-symmetric, they would be symmetric, which wouldn't be something that we would want. So this would be an anti-symmetric wave function. I mean, wave function, electron wave function, which means it obeys the rules of fermions. Okay, so this was a question at my last exam, which was one of the hardest questions when we ever had. But after looking at it again, it's really kind of straightforward, and I think you can definitely do this. If something like this comes up, and I think you guys got this for like a quiz, like something like this on a quiz. To look over. So let's say we have beryllium 2+ cation comprising of an atomic nucleus with 4 protons and 2 electrons moving around the nucleus. Write an expression for the electron Hamiltonian 1-2 of beryllium 2+ in atomic units, what all kinetic and potential energy terms shown explicitly. So what we would do is get this term here. So beryllium 2+. All right, so beryllium has 2 electrons, which means that after you remove those 4 electrons. So after you remove those 2 electrons, we're gonna have 2 electrons. After removing 2 electrons, we have 2 electrons, yeah. And so we can write down the term for this. So since there's 2 electrons, there's gonna be 2 terms for the kinetic energy. So we have -1/2, 1 squared, and -1/2. Okay, and that's squared. And so we got 2 terms here, and we're gonna have another 2 terms. Oh, wait. So it's gonna be, let's put this -ZR1 and plus -ZR2. Okay. And since we have 2 electrons, the electrons can only interact to each other and can't interact twice to each other. So we're going to only have 1 term. So it's going to be R12. Now, does anyone have any questions on how I got this? No, there's something in the chat. Everyone's good with this? All right. All right, given the difficulty of solving the Schrödinger equation for the system, at this stage, we decided to study electron properties of beryllium 2+ cation by permutation theory. Identify which terms in your results in part A would include the reference H1, H0, and which terms would you include in the permutation? Okay, so from here, we just look at stuff that isn't that's new to us. So we saw that these terms here are familiar with us. These are the terms that helped us get the original H-like atom. Yeah, H-like atom. The H-like atom before. So that originally gave us the 1 electron. So this would just be, this whole thing would be H of 0. And this H of 0 has 2 terms. It would have H of 0 for 1 and H 0 for 2. And this would describe the first electron, and this would describe the second electron. Okay. And over here is the new term that we have, because because of the interactions of electrons, we have to make up a new term to to account for them. And so this is just going to be H, the new term that corrects this equation. Okay. All right, for part C, let me just pull up. Okay. Okay, so the next part is asking us to basically propose a zero order wave function for the ground state of beryllium 2+. So since this is a zero order, this doesn't include anti-symmetric wave functions, which means we can write a symmetric wave function just fine. So for C, if they ask you something like this, just write down this. So we can just write down a multiplication of the spatial part. So it's 1SA1 and 1SB2. So 1 over rad 2. Beta 1 minus, that's plus. So we could totally suggest this as our wave function here. Okay. Let's see. Propose an approximate zero order wave function for one of the lowest energy excited states beryllium specifically. Consider a ZX state for which the space part of the wave function is symmetric and the spin part is anti-symmetric. Under exchange, effectively the spatial and spin parts of the electrons. Okay, so for part D, so it's telling us that the spatial part is excited state. So we could pretty much write the same wave function, but this time that it's telling us that the spin part is anti-symmetric and the spatial part of the electron is symmetric. So what we can write is instead, looking at this, let's think about this. What we can write instead is let me think about drawing the orbitals here. So this is an excited state. So this is going to be 2 electrons. But this time it's going to be 1 here and 1 here. And this is going to be 1s and 2s. And because of that, we have to account for if we can't just write the we can't just write this. Because if we write this, then if we apply the operator, then this will just be 2s2 and 2s1, which is not equal to our spatial part that we suggested here. So to account for this, we have to make a linear combination of both probabilities of the electrons either being in electron 1 being in 2s, or electron 1 or electron 2 being in 1s. So we can write down the spatial part as this. Give me 1 second, guys. Let me just so. Okay, sorry about that, guys. Okay, so what I was saying before is you can't suggest that the wave function look like this, because when you exchange them with this operator, you're not going to have the same wave function. So you have to make a linear combination of both probabilities of electrons being in either one of the other orbitals. So what you write down is 1 over rad 2 can be, because they're symmetric, they have, oh wait, because they're anti-symmetric, they have different spins, yeah. And then what you write is 1s1 and then 2s2, and that's plus 2s 1, and then that's 1s2. And I'm not going to show this, but if you apply the operator, this is going to be symmetric. And the spin part of 1, 2 is just going to be equal to just the same equation as before, but this time it has a minus sign because it's anti-symmetric. All right. Okay, so based on that, we can just write down the wave function. And I'm not going to expand anything, but it's just basically a multiplication of both of these. Okay, does anyone have any questions from this? Any at all? Because this is like a little confusing topic here.
I have a quick question. Actually, it may not be that quick, but how is there a formula you're following? Like, how do you know that it's like, how are you just coming up with the 1s1 numbers?
Oh, okay. So, oh yeah, I kind of just like learned it from memory, but there is a rule you can say. I think I put it here, but sorry, give me 1 second. I don't completely remember what the rule was, but it's something like in a situation like this, like I can just tell you that you would use, like, if they're both in different orbitals, then you would use this equation here. But if they're both in the same orbital, then you can use just a multiplication of this. And I'll just write it down here. So it's called Slater, I think it's called Slater conduct rules, but I don't think did you guys learn that yet, actually? I'm not really sure if you guys learned that, but that's a really long thing that I'm not gonna get into, but let me just say this. So let's say that we have in the same orbital, you can write the wave function as, let's say, a multiplication of these. So it would be like 1s. If there are two electrons and there are two different orbitals, you can just write like 1s1, 2s2 plus 2, that's 2s1. So if you have something like this, like if they're both in the same orbital, you can write it like this. And if they're not in the same orbital, you can write it like this. And if they're saying that the electrons are antisymmetric, then you can write it like this, with a minus sign. Does that make sense at all?
Yeah, so are those like equations? It doesn't matter what the atom is, right? It doesn't matter that it's beryllium.
No, it doesn't matter. It just matters orientation and they're symmetric or antisymmetric.
Okay, and this is based off like the spin part being asymmetric, right? So what about the wave function? Does that matter if it's symmetric or asymmetric?
Oh, if they tell you that the wave function, like the spatial wave function, is antisymmetric, then you would just put a minus sign here, and this would be a plus. Does that make sense?
Yeah, thank you.
No problem. Okay. So does anyone else have any other questions or everybody good? Okay, so I think I'm approaching almost the end. And this is going into more detail about what I just explained on antisymmetry. You guys can see the cases here in the examples, but basically just explaining just the excited state, how this must be one wave function has to be symmetric, one has to be antisymmetric. And let me just go to the next thing. And this part really doesn't matter. I just put it here because it was like in my notes. And okay, last part is the variational principle. So let's say you have, it's kind of like permutation, but not really. So let's say you have a wave function, like a trial wave function you want to use. It has the same boundary conditions as the wave function. Like let's say you have a trial wave function that's kind of like particle in the box, and it's kind of like particle in the box. It has to have the same boundary conditions, and it has to have the same boundary conditions, I'm pretty sure, and it has to follow the rules of a wave function. So it has to do stuff like as it approaches let's say 0 order boundary conditions, or it has to be continuous. So okay, so if you have the trial wave function, you can solve for an energy of it, but we don't know we can't get the expectation value from it normally. So what we do is we find the expectation value normally here, and then we divide it by its interval. And this trial function may not be normalized, so you have to solve the integral for this. Okay, and the steps here for how you do this is shown. Oh, is there a question? Okay, all good. All right. It's shown here. So this energy that we solve for is basically like a trial energy that we have for our trial wave function. And the closer it is to the thing we're modeling, the more accurate it is. So I'll show this here. So it's greater than, so it's always greater than the energy we're comparing it to. So if it's a trial wave function for a ground state particle in the box, which is at n=1, it will be the more accurate it is to that energy, the more accurate the trial wave function is, or more accurate the energy is too. Yeah, and then so the steps to this would be to calculate the Hamiltonian applied to the trial wave function, which is probably going to be like the second derivative or something. And then we have to also calculate the integral for the trial wave function onto itself. And then we also evaluate, this by dividing these two terms to each other. And after doing that, if there is a parameter like b, what we do is we solve the integral normally, and then we put it in terms of that parameter, for example, like b, and then we solve for 0. And by minimizing it, we're getting it close to that energy. And then we put, after solving for b, we then plug it into the original equation. Okay. So what I'm gonna do is I'm gonna solve the first part of this question, and I'm gonna leave it there. And if you guys have any other questions, I can you'll answer them, or any questions you want me to try out. So let's try this. So consider a trial wave function. This here, calculate the variational energy for particle in okay, so this is model active particle in the box. So what we do is we solve for this. Okay, and so first things first, we apply the operator. Onto the trial wave function. And this is going to be, I think, h bar squared over, I think it's over 2m second derivative. And let me just double check the Hamiltonian operator. Okay. Okay, and I am right, just need a negative here. Okay. And this is going to be applied to our trial wave function, which is nx over L minus x. Okay. And then we take a second derivative of this. So I don't want to deal with any product rules. So let's just simplify this to n Lx minus x squared. And then we get negative over 2m. And we take the first derivative of that. This is going to be n times L minus 2x. And then we do negative h bar squared over 2m. And to take another derivative of this, which would be n minus 2. Okay, after solving for this, this will just be equal to plus L2, and this will be positive h bar squared over m times n. Okay. So then we solve the integral for this. So the integral from 0 to L, and we solve the this is the trial wave function, which is just nx. And I'm going to distribute this in, so it's going to be Lx minus x squared. And this is just the integral result. I mean, this is the Hamiltonian operator result, so it's just going to be n h bar squared over 2. And this will equal to n squared times h bar squared over 2. 0 to L, and this would be Lx minus x squared. Okay, and then from here, we just solve the integral. This would be n squared over h bar squared over 2, and then this was 0 to L. Lx squared over 2 minus x to the third over 3, 0 to L, and that would be equal to L times L, so it's like L squared, L to the third over 2 minus L to the third over 3. Okay. This would be the first part, and this would just be L. Okay. All right, and then from here, we just solve it, and then we would just get n squared h bar squared over 2, and then that would be L to the third over 6. Okay, and that's what the numerator, we just solved for the numerator here. And for the denominator, and now for the denominator, we just solve for this part. And this is just 0 to L, and this is just going to be the wave function squared, which is just nx squared times L minus x squared dx. And we're just going to simplify this, expand it out, and keep the constants out. Lx. Make sure we're wrong. Okay. Since this is x squared, you can put this inside. So this would equal to 0 over L, and this would be n squared on the outside. Then you would have L x minus x squared squared dx. Then distributing out L squared times x squared minus 2L x to the third and this would be plus x squared, x to the fourth, I mean. And then from here, we would solve the integral, which would be n squared 0 to L out to this, also the third times x squared times third over 2 minus 2 L x to the fourth over 4 plus x to the fifth over 5. All right, I'm gonna end it off here for this question. Oh, nobody left.
They all left.
Yes, they all left. That question was freaking long, variational theory. Don't even know why I did it. They were dropping like flies throughout the entire time. So,
I mean, it was in and out. I was looking at the Zoom calls. It was like people joining and then rejoining and leaving and rejoining.
yeah, I might as well cut the variational theory out and just can you cut that out actually? No problem.
Okay.
If that's cool.
I'm like on the floor right now.
Oh, just do it, I guess tomorrow.
Yeah, I'll upload it.
The full amount. That was a long review. I think that was like 3 hours, right? 2
It
hours.
was two, almost two.
Oh. Damn.
No, we're at two, yeah. Okay, so take it, get the rest you deserve and make me host so I can like process this.
Yes, sir. Make a host. Sir.
Thank you.
How was your trip, by the way?
It was really good.
That's good, my friend. Sorry you got sick.
Yeah, it's whatever. Oh, you needed to stop recording.
Oh. I forgot.
Yeah, I got sick on literally the way back. I stopped in Minneapolis, had some chili, and I woke up at 2 a.m. just in agony.
What was within that chili, man?
I don't know, man. It was beef. It didn't taste good. It was weird.
If a chili doesn't taste good, there's no point of having it. Or man, I'm actually sick of this.
Okay, I'm gonna end this, dude. Thank you so much for doing this. I'm sorry that I couldn't do anything more, but I took a moment to throw up.
It's fine, my friend. You just get better.
Thank you. Okay, see you around.
See you, good chum. Tell me how it goes with you.